In this video, we'll take a look at problem number 23 from out of section 2.2. And if you watched the last video, we were starting with the graph of a function, and we were trying to sketch the graph of that function's derivative. Here we're basically doing the opposite. We're starting with the graph of f prime. So this is a graph of a derivative, and we want to try to use the graph of this derivative to sketch the graph of the corresponding function. The reason why this plausible word is here is because when we looked at this in class, we decided that the information we can take off this graph will tell us the shape of our curve, which direction it's traveling, but it won't really tell us where it's located within the coordinate plane. So we can move a curve of a particular shape up, down in the coordinate plane, and the slope of the tangent line at any x value you look at, it'll still be the same as if the y value at that point was negative 50 or the y value was positive 50. So it's a plausible curve because the shape of the curve can be determined by this, but the location, way up here in the coordinate plane, way down here in the coordinate plane, we can't really determine based on what we're given access to. So what I like to do when I'm attempting to go from the graph of the derivative to the graph of the function is I like to see if I can label these intervals, okay? Are there any places on the function that we're about to sketch here where the slope of the tangent line must be 0? And if you look at the graph of our derivative, there's one spot over here where the derivative crosses the x-axis, where the derivative's value is 0. So this is a spot where the value of the derivative must be 0. I'm going to go ahead and just kind of scale my axes here. So I'm going to call this negative 1, I'm going to call this negative 2, I'm going to call this positive 1, I'm going to call this positive 2. Okay, so I've done a pretty pronounced scaling. I haven't really put my tick marks close together, and I kind of needed to do this to answer the questions down below. So if you try number 24, which would be right after this one, and it's the same type of problem, you can definitely do what I've done here and just kind of scale your axes however you see fit. But at negative 2, since the value of f prime is 0, I know that this is a spot on my graph where the slope of the tangent line must be 0. So I've either got to have a graph that's completely leveling off, and I need to have a graph that's completely bottoming out at negative 2 or completely topping off at negative 2. Either way, it's got to be leveling off. I want to know where the slope of my tangent line is negative. F prime gives slopes of tangent lines. F prime is negative here, F prime is negative here. So I guess the slope of my tangent line would be negative at any x value to the left of negative 2. So I'm going to indicate that in interval notation. So from negative infinity to negative 2, the slope of my tangent line is going to be negative. And then also from 1 up to 2, not including 1, my slope would be negative. And actually, I'm going to assume this extends to the right, so I'm going to say the slope of the tangent line is also going to be negative from 1 up to positive infinity. And then where's the slope of the tangent line positive? Well, the slope of the tangent line is positive here, anywhere where the derivative's value is positive. And the derivative's value is positive on this portion of what looks to be a parabola, and that would be from negative 2 up to 0. And then it would also be positive from 0 up to 1. The one tricky thing here is trying to decide whether or not you can include 0. And if you look at the graph of the derivative carefully, neither of these are closed circles. So the derivative actually isn't defined at 0. And whenever we spoke about a derivative not being defined at a given location in class, what we said that would probably represent would be a cusp on a curve or a jagged point on a curve. So I'm thinking that based on what we can kind of infer from this graph, we probably have a cusp at x equals 0 on whatever we sketch. And for the same reason, I mean, I didn't consider this because we have a change from positive to negative with the sign of the derivative at 1, but look, neither of those circles are closed. So I'm thinking we probably have a cusp at 1 because the derivative is not defined at 1. So it seems like we're going to have a cusp at 0 and another cusp at 1. And remember, a cusp is just a sharp point on a curve. It's a spot where the slope of the tangent line is undefined. Now if we try to take this information and bring it back up into the coordinate plane here to sketch ourselves a graph, we should be able to do that. We don't really know exactly where this graph is located, if it's located way down below the x-axis, way up above the x-axis, because all these things tell us is basically the shape of the curve. So I'm going to do the same scaling here as I did on the derivative. I'm going to call that -1, -2, 1, and 2. And at -2, I have to have something significant happen. I have to have the graph completely bottom out or completely top off. And if you look at what happens at -2, the slope of the tangent line changes from negative on the left side of -2 to positive on the right side of -2. So if the slope of the tangent line goes from negative to positive, I guess at -2, negative to positive, I guess at -2, I have to completely bottom out. So I'm just going to put a point here, and I don't know if that point's on my graph. I just like to get an anchor point on my graph, but this graph could be moved up, or down, way down in the coordinate plane. I need to have my graph completely bottom out at the x value of -2, right? We go from the slope of the tangent line being negative to the slope of the tangent line being positive as we cross this value, and we have to have a horizontal tangent line at -2. And based on what I've drawn so far, this accomplishes that. Now as we go towards 0, check out what has to happen. Slope of the tangent line is going to have to be positive, and it's going to have to get steeper, 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 but then we have the steepest positive slope at some x value that's, I don't know, maybe -2/3. The biggest value of the derivative is right here. So the steepest positive slope has to happen somewhere in here. So I'm going to just try to draw something where the slope's increasing, 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 but then my graph's going to take a little bit of a change, because the slope of the tangent line, although it still has to be positive, it's got to start to level off a little bit again, because the value of the derivative is not quite as positive here as it was just a little while back. So my graph is leveling off ever so slightly as I cross the x value of -2/3, and I have to keep that positive slope until I get to the x value of 0. So there's positive, positive, beginning to level off slightly. And then at 0, what I have to have happen is I have to have the slope of my tangent line go from being, I don't know, whatever this is, maybe +1, to being +1/2. So if I'm saying that this is where y is +1, then this would likely be where y is +1/2. Slope of my tangent line at this point has to go from +1, level off a little bit, and it's going to be kind of hard to show this because I haven't really drawn this very steep. I'm going to have the slope of the tangent line stay positive but level off slightly. So if I would have gone back and tried this again, I probably would have drawn something that would have looked like this. Steeper, 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 level, 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 and then at 0, what I need to have happen is I need to have the slope of the tangent line go from +1 to +1/2. So we rapidly change from the slope of +1 here to the slope of +1/2. So it's not a very jagged point on the graph, but it is a slight rigid point on the graph. And then the slope of the tangent line is constantly 1/2 on that entire interval. So the graph is just going to be working its way upward ever so slightly with a slope of +1/2 until we get to 1. So this was bad, because at 1, this is why you should always do your math in pencil, by the way. At 1, we have the slope of the tangent line become negative, given by the negative value of the derivative here. So at 1, the slope of the tangent line maybe goes to -1/2. So we have another little cusp at 1, and then we have a constant slope, right? We know it's constant because if you look at the value of the derivative, it's always the same. It's not moving up or down the value of the derivative here, so it's constantly that same value. So this is how you can sketch the graph of a derivative given the graph of a function.